Hello friends, in this last few lectures of this course, we've been considering ways to enhance the creep resistance of the material. So by enhancing the creep resistance of the material, we want to improve the life of the material in its high temperature application. So primarily, we have been addressing this particular problem of enhancing the life of the material by restricting the mobility of the dislocation. So the initial approach that we considered involved including a solute atom in the lattice of the base metal, and depending on the distortion this solute atom brings, there will be an elastic interaction, and this elastic interaction impedes the movement of the dislocation, thereby restricting the amount of plastic deformation exhibited by the material at a given point within the steady state condition. So when you restrict the amount of plastic deformation exhibited by the material for a given stress within the steady state condition, you are essentially decreasing the already minimal creep rate exhibited by the material in the steady state condition. So when you further decrease the creep rate in the steady state condition, you are extending the duration by which the material spends its time, or during which the material spends its time in the steady state condition. So thereby you are enhancing the overall life of the material at the high temperature. Now this we saw can be achieved. One of the ways is that by introducing a strong elastic interaction between the distortion brought about by the solute atom to that of the distortion that is implicitly associated with the dislocation. These two elastic distortions, they interact and they impede the movement of the dislocation. The other way this can be achieved in the framework of the solid solution strengthening is that it changes the material property to some extent. However, this is not that much effective at high temperature. And there are one other interaction that helps to impede the movement of the dislocation in solid solution strengthening is this electric interaction because of the difference in the valency of the solute atoms and the base metal atoms. So when there is a significant difference in the valencies, the positive charge associated with each of these metal ions, they will be significantly different, and this difference in the positive charge associated with the metal ions, they interact and they impede the migration of the dislocation. And finally, we saw in the context of the solid solution strengthening, it is possible for us to impede the climb of the dislocation. When we talk about the climb of the dislocation or the movement of the dislocation, what we are essentially doing is by dislocation, since dislocation is a line defect and it propagates in the form of the line, what essentially we are talking about is the introduction of stacking fault. Locally, we are introducing a stacking fault. Now, because we are in the solid solution strengthening, there is a solute atom that has a size that is significantly different from that of the base metal atoms. Even though this will violate your Hume-Rothery's rule, this size introduces a significant amount of distortion, and that is why, despite the restriction in the solubility, we are introducing it. So because of this difference, in case of the substitutional solid solution, you have an atom, solute atom, that has a significant difference in size present in the base metal lattice. So this increases the stacking fault energy that is associated with the climb or movement of the dislocation. So because of this difference in the size and because of the distortion that is brought about, and since the climb event and the movement of the dislocation should involve the larger solute atoms, the stacking fault energy is correspondingly increased. So therefore the mobility is restricted. When we talk about the solute atoms, when it is considerably, size of it is considerably smaller than the base metal, you have interstitial solid solution. In case of the interstitial solid solution, what you essentially have is interstitial atoms spinning the movement of the climb event of these dislocations, and therefore also consequently increasing the energy that is required to bring about this stacking fault that will be introduced when the dislocation climb. So therefore, both substitutional and the interstitial solid solution, they bring about or they affect the mobility of the dislocation by altering the stacking fault energy locally. So these are the different ways solid solution strengthening helps us enhance the creep resistance of the material. So most of these ways have to do with restricting the mobility of the dislocation, and only one way has to do with changing the property of the material in the framework of solid solution strengthening. The change in the property does not have much effect at high temperature. Now, in the previous lecture, we considered introducing another phase, introducing second phase to enhance the creep resistance. Now, when you introduce the second phase, we saw that there are several factors that govern the role of the second phase in the base metal or in the parent phase. So, when you introduce the second phase onto a parent phase, there are several factors that governs the change in the behavior of the material. Now, these factors, they include size, shape, number density, distribution, and of course the properties of the second phase that you are including. So, generally we have confined our restriction to the combination of phases wherein the parent phase is ductile in nature and the secondary phase that we are introducing is hard and high strength material. So, its ductility is rather compromised, but it is hard and a high strength material. Now, what we essentially now have is you have a system with two phases, and the way the second phase it distributes itself depends or it governs how the creep resistance or the mechanism by which the creep resistance is enhanced. Now, the second phase, it is possible for the second phase to have to assume a grain of its own, to have a size that is comparable to the average grain size, and it can be formed or it assumes a shape of a grain of its own. So that means it establishes a two-phase microstructure, or it establishes a two-phase system. So the principal factor that governs the introduction or the way these second phases are distributed, it renders two different types of microstructure. One is the two-phase microstructure. So the features that render this two-phase microstructure is the size of the second phase is more or less similar to that of the average grain size, and the shape of it, it forms a shape that is more or less renders a continuum that you observe in any other grains. So you have a two-phase microstructures, and here the grains are not homogeneous, chemically homogeneous. For each of these grains, they are associated with one of these phases. And now we saw in such a condition, what you essentially have is you have essentially changed the material from a single-phase material, homogeneous material, to a two-phase material. So that means the property correspondingly changes, and therefore the behavior is enhanced. So when you introduce an appropriate phase as the second phase, then you can enhance by the appropriate combination of the matrix phase and the secondary phase. You will be able to enhance the creep resistance just by enhancing the properties. So far there are two ways you can enhance the properties. One is by impeding the dislocation moment. The other is altering the property of material. So the altering the property of the material is rather dictated by the materials that you combine, the phases that are present. So therefore, when you have an appropriate combination of the phases, you will be able to enhance just by the properties of these combinations of phases. You will be able to enhance the creep resistance. So other is the impeding mechanism, and we saw because of these difference in between the two phases, in addition to the misorientations that introduces the grain boundaries, crystallographic misorientation, when you have two phases, the interface that separate two phases are separating two different chemical compositions, two different crystal structures. Therefore, there is a significant amount of strain energy that is accumulated. So therefore, the dislocation moment is impeded. So the plastic deformation is restricted, or the plastic strain is restricted. So we have in this framework of two-phase microstructure, and also in case of solid solution strengthening, we saw there are two ways one can enhance the creep resistance, impeding the dislocation and altering the properties. In case of solid solution strengthening, the property that was altered does not play a significant role because not much was altered. But however, in case of two-phase microstructure, you are essentially talking about a new system. Therefore, the property is significantly altered. So when you have the right combination, right phase fraction of different phases, you will be able to enhance inherently the creep resistance. In addition to that, you have, because of these difference in the phases, crystal structure, chemical composition, and also the orientation along with it, because of these difference in the features, you build up or accumulate sufficient amount of strain energy in the interface separating these two phases, and they interact with the dislocation and also impede their movement. Now, this is just one way of establishing or introducing a second phase into the homogeneous single phase system. Again, we are talking in terms of a homogeneous polycrystalline system. The other way is to introduce the second phase in the form of particles, and there are two ways of introducing it. This means that you now still have more or less a homogeneous system. However, the homogeneity is now disturbed by particles of the second phase present. So these particles can either be present along the grain boundaries, and also they can be present within the grains. So they are distributed, or they are present in the region where which is surrounded by the homogeneous orientation of the grains, that is within the grains. Homogeneous orientation of the atoms, that is within the grains or along the grain boundaries. So this distribution, this dispersed distribution, is much different from the two-phase microstructure, where the second phase was rather confined to a specific region, and these regions were distributed, and these regions were similar to that of they had the size that is similar to that of the average grain size. But in case of particles, they are significantly, their average size is significantly lower than that of the average size of the overall material, average grain size of the overall polycrystalline system. Now, the way these particles are introduced into the system, we saw there are two possible ways. One is precipitation hardening. I will just write it as PPT, precipitation hardening. And the other is the dispersion hardening. So in case of precipitation hardening, this depends on the relation between the solubility and temperature. Meaning, at high temperature, a given solute will be highly soluble, and when you reduce the temperature, the solubility is decreased, and this solute is expelled out, and these solute form these particles. So particles are nothing but the solute-rich phases, and they form at low temperature, and because of the difference in the solubility. The solubility is decreased, the solute is expelled out, and the particles are formed. Now, the drawback of this particular precipitation hardening is you have to be very careful. This is purely a material governed property, material governed behavior. If you have to be very careful on, you have to be very selective on which material to use, and on which solute to use, or which base metal to use, and which solute to use. And you cannot combine you cannot have any combinations of phases. You are restricted by the combination of phases that can be produced by precipitation hardening. So you cannot have any different combinations. The combinations again are restricted by the solubility of the base metal. And now, when you have the influence of solubility on the temperature, it is also possible that at high temperature, the one that we are interested in, these precipitates that are formed because of the difference in the solubility can dissociate back to the base metal as you increase the temperature. So you have to be very careful on the operational temperature, because at that temperature it is possible for the precipitate to dissociate or dissolve back into the base metal. So these are the two restricting points of using precipitation hardening to introduce the second phase in the form of particles into the base metal. So the other approach is the dispersion hardening, wherein it is primarily processed by the powder metallurgy technique, wherein you have particles of different phases that you want to combine. You process it in such a way that you establish a continuum, and these particles are dispersed within the base metal or the base continuum. Now, by this approach, you can achieve, at least theoretically, wide range of combinations of phases, and you can dictate the size of these dispersed particles. Now, since it is not the whole principle of formation of this combination of the particles and the base metal is not dependent on the solubility of these solute and the difference in the solubility with respect to the temperature, we can achieve different combinations of phases, and these combinations of phases are not disturbed by the change in the temperature. So therefore, the dispersion hardening is much preferred than the precipitation hardening when you want to increase the creep resistance of the material. Since the processing technique varies, and therefore you have a wide range of combinations, it is possible, at least theoretically, to have a wide range of combination of phases, and on top of it, this combination of phases, particularly the phase fraction size of the phases, is not disturbed by the temperature. The dispersion hardening is considered preferred for producing the microstructure with dispersed precipitate that enhances the creep resistance. Now we saw, in order to understand the way these dispersed particles affect, irrespective of which way you produce it, precipitation hardening, dispersion hardening, Irrespective of it, now we are talking about the mechanism by which these precipitates, these particles that are present in the base metal continuum, in the polycrystalline material, we want to see how it influences or enhances the creep resistance. For that, it is important for us to understand the different interfaces these particles form with the base metal. So we saw in the previous lecture, there are 3 different interfaces these particles form with the base metal. We refer to them as coherent interface, incoherent interface, and semi-coherent interface. Now, this distinction can be brought about by considering the continuity of the atom across the interface. So you have an interface that separates 2 different phases. The particle and the base metal is separated by an interface. Now, if you can track the continuity, or when you consider tracking the continuity of atoms across the interface, then based on that action, you will be able to distinguish the interface that separates 2 different phases. When it is possible for us to track a continuity, then you end up having a coherent interface. So when it is possible for us to track the continuity of the atoms, what you essentially have is a coherent interface. However, when the continuity is not present, maybe because of the difference in the sizes of the atoms or the way they are arranged, their crystal structure, and we talk about sizes in the atoms, meaning the chemical composition of both these phases is significantly different, that we are not able to identify any continuity, then you end up having an incoherent interface. Now, when there is a continuity that is being established by an introduction of some defects, then what you have is a semi-coherent interface. So you have coherent, semi-coherent, and incoherent interface, and depending on the continuity, this can be established. Now, other way of introducing or quantifying this interface is by considering the difference in the interplanar distance. Supposing you have 2 phases that are separated by an interface, and you can calculate the interatomic spaces, or you can also calculate the distance between the 2 planes. So these planes are nothing but the atomic planes, and these planes are the one that vary in accordance with the crystallographic orientation. So you can calculate the interatomic or the interplanar distance, and based on the interatomic or interplanar distance, so when I say interatomic, it means that the distance between the atoms, wherein the atoms are associated with a specific plane. So these terms can be used synonymously, provided you are considering the atoms in a specific plane. So you can calculate or quantify coherent, incoherent, and semi-coherent by calculating the interplanar distance or interatomic distance. Now, if A alpha and A beta are the interplanar distance for phase alpha and beta, the coherency or the nature of the interface can be considered by, or can be quantified by considering the difference between these interplanar distances between the 2 phases, and considering with respect to one of the phases. So this can be also replaced by A beta. So you are considering the difference in the interplanar distance between the 2 phases with respect to one of the phases. It can be alpha or it can be beta. So either alpha or beta can be in the denominator. And of course, you are taking the percentage of it so that you can talk in terms of 1%, 20%, and so on and so forth. So just you can take the percentage of the values with respect to a given phase. So by calculating the interplanar distance between the 2 different phases, you will be able to quantify, or you will be able to designate if a particular interface is a coherent, semi-coherent, or incoherent interface. Now, when the difference in the interplanar distance is close to 5%. So when it is close to 5%, it's not much, but it is close to 5%, then you have a coherent interface. Of course, this percentage vary depending on the materials, and also if you want to have a specific understanding of this coherent and incoherent interface. So therefore, since this is dependent on the material, and this is also dependent on the applications that these materials are being used, different literatures, they refer to, or they distinguish these misfits in a different way, or these differences in a different way. They categorize it in a different way. The range different interfaces vary. So this is one of the common thread that you can find, that when the difference in the interplanar distance is close to 5%, it is not more than 5%, it is close to 5%. So the thing is that there is no definite ranges. Of course, there are definite ranges for the extreme limits, and there are definite ranges for the limits in between, but for coherent it is just stated that the difference should be small. So one approach is to consider it to be 5%, and I have found literatures wherein they have considered 2%, 1% as well. They have considered 2% as coherent as well. So 5% has been set, the maximum is 5% has been set as the maximum. So in that case, when the difference in the interplanar distance is close to 5% or is around 5%, then you can refer to that interface as the coherent interface. So you have an interface separating alpha and beta, and the difference in the interplanar distance is close to 5%, then you have an coherent interface. Above 20%, what you have is an incoherent interface. So in case of 5% and below, you have coherent interface. Above 20%, you have incoherent interface. Of course, this I've also seen literatures where this has been treated as 25% as well. So again, since this is a range, you have some wiggle room. Now between these two, that is between 5 and 20%, whatever you have will be a semi-coherent interface. So it is possible for us to quantify by considering the interplanar distance to quantify the coherent, incoherent and the semi-coherent interface. Now the reason we have quantified this is because this tells us how much of a mismatch is there between atoms in one phase with respect to the atoms in other phase. So let us begin by considering the coherent interface. In case of coherent interface, of course, there is a mismatch, and this mismatch ranges is up to 5%. So this is nothing but is the difference in the interatomic distance or interplanar distance. So this can be referred to as the mismatch. So this expression here can be referred to as the mismatch. And now, even though it is a coherent interface, what we are considering is a coherent interface, and it is possible for us to trace some sort of a continuity between the atoms in one phase and another, since there is a mismatch. However, despite this continuity, there is a mismatch that characterizes this coherent interface, and this mismatch is around 5%. So this mismatch, when you have such a mismatch, even though it is low, there is a strain energy associated with it. So when we talk about strain energy, what it means that there is an elastic distortion associated with it. So you have essentially introduced a particle, and this particle shows, or the atoms in that particle shows some continuity to the atoms in the matrix phase. However, even though there is a continuity, there is a mismatch in the heteroatomic distance that introduces a 5% of a mismatch, and therefore this mismatch it gets translated into a strain energy. So what it means that despite being coherent, there is a certain amount of strain energy associated with this particular interface. And now when the dislocation reaches this particular phase and also correspondingly this interface, there is an interaction between the strain energy that is associated with the dislocation and the strain energy that is introduced because of the mismatch. So again, we have an elastic interaction, and again similar to that of the solid solution strengthening, here the elastic interaction between the strain energy that is introduced because of the mismatch and the strain energy that is introduced or that is associated with the dislocation, you have an influence of this particle on the moment of the dislocation. So this particle impedes the dislocation. Additionally, once this interaction is largely confined to that of the interface alone. So once the dislocation moves into the particle, the way it behaves considerably varies. Let me repeat, this particular interaction is confined to the interface between the particle and the parent phase alone. So once the dislocation has overcome this particular interaction and it has moved to the interface, the way it behaves considerably varies. So it is important for us to consider the behavior of the material as it crosses this particular particle. So we are not just confined, or we are not confining ourselves to the interaction between the interface and the dislocation, but we also want to see, in addition to this interface, we want to see how the particles interact with the dislocation. Now, if you consider a coherent particle like this, and you have a dislocation line that is propagating towards it, so when it reaches this interface, there is an elastic interaction. And however, when in addition to the elastic interaction, that this particular dislocation, it interacts with the overall particle as well. So since the crystal structure and the chemical composition of all of the particle is significantly different from the base metal, the slip system will also vary, and the way this particular dislocation line, that is like shown in red, it interacts with the particle also varies. And it is important to note that since this particle is a brittle one when compared to the matrix, as the dislocation propagates, this particle breaks, and therefore what we end up having is, as the dislocation propagates, you would have, instead of one particle, you would be having two particles, and this would have been brought about by the propagating dislocation. So the dislocation, as it reaches the interface, you have elastic interaction. This impedes the rate at which the dislocation is propagating. In addition to that, the dislocation also interacts with the overall particle, and it breaks the particle. So in addition to the restriction in the movement of the dislocation, or the restriction in the rate at which the dislocation moves because of this particle, what you essentially have is, as a considerable amount of stress is being spent in the breaking of this particle, in fragmenting the particle, the considerable amount of stress is being spent. So you have an interaction between the dislocation and the interface, and there is an interaction between the dislocation and the whole of the particle. Now this interaction, elastic interaction, it impedes the rate at which the dislocation propagates, and the interaction between the particle and the dislocation that ultimately fragments the particle. This is referred to as the Friedel cutting. This phenomena is referred to as the Friedel cutting. So what Friedel cutting does is, it consumes a sufficient amount of driving force that dictates the movement of the dislocation. So therefore, this also contributes to the, this also restricts the propagation of the dislocation. So there are two phases, there are two ways coherent phases, it restricts the propagation of the dislocation. One is through the elastic interaction between the interface that separates the phase and the matrix phase, that separates the particle and the matrix phase. Because of this elastic interaction, the rate at which the dislocation moves is impeded. Secondly, in addition to this interaction, you have the whole particle that is interacting with the dislocation, and this particle, because of its nature, since it is brittle in nature, it breaks up, it fragments, and it ultimately consumes, or the reason for the fragmentation, the energy required for the fragmentation is consumed from the dislocation. So therefore, the effect of stress within the or surrounding the dislocation, that is effect of stress that is available for it to propagate, the driving force that governs the propagation is now reduced. So by interaction with the interface, and also by the interaction with the whole of the particle, now the propagation is impeded. So we have now seen two ways already how the dislocation can be impeded, how the plastic deformation can be restricted, thereby enhancing the creep resistance. One is by altering the property of the material. So in two-phase case condition, the whole of the material, the property is adjusted. So that means by the property alone, by changing the property alone, you can enhance the creep behavior. Secondly, we saw when we impede the migration of the dislocation, the rate at which the dislocation moves, you can enhance the behavior or the creep resistance of the material. Now thirdly, now we saw when we allow the dislocations to interact with the particle, the driving force is considerably reduced, and therefore the dislocation cannot move as easily as in case of the homogeneous material. So even though this ties up to the restricting or impeding the mobility of the dislocations, now this is achieved by reducing the driving force, or because of the interaction between the whole of the particle and the dislocation. So this is a way coherent particle influences or enhances the creep resistance as a whole. So by the interaction between the coherent interface and the dislocation, so that way they impede the movement of the dislocation, and when the overall particle it interacts with the dislocation, considerable amount of the driving force that dictate the propagation of the dislocation is consumed for the breaking up or fragmenting of this brittle particle. So in both these ways, the creep resistance is enhanced because both these ways reduce the rate of plastic deformation. So both these ways reduce the plastic deformation at a given time. So in both these manner, that is elastic interaction and interaction between dislocation and the precipitate, we can reduce the rate of plastic deformation, or we can reduce the amount of plastic deformation, and we can enhance the creep resistance of the material. Now, in case of, we will go to the incoherent case. So in case of incoherent interface, the difference in the interplanar distance is greater than 20% and greater. So in that case, the strain energy is also sufficiently higher. So since the strain energy is sufficiently higher already in the interface between the particle and the parent phase, in that interface, since the strain energy is already higher, this interaction between the dislocation and the interface is it's averted, because energetically you already have a highly strained region, and the dislocation, which has a distortion of its own, will not interact with this highly strained region. That is not energetically preferable. So you have a very high amount of strain energy because of the incoherent nature of the interface. So therefore, the dislocation which has a strain energy of its own will not interact with this interface, which is already is an highly strained region. So you have a dislocation that is coming towards a particle, and the interface of the particle is a highly strained region, and because it is a highly strained region, and the dislocation is implicitly comprises of a strain energy of its own, it will not interact. But instead, the way it interacts, it will not interact directly with the interface, but the way it interacts with the particle as a whole. So similar to the first consideration that is moving towards the dislocation, or rather the dislocation is moving towards the particle, and this particle has an incoherent interface, meaning there is a considerable amount of strain energy that is present surrounding this interface. So there will not be a direct interaction between the dislocation and the interface because of this high amount of strain energy. So what it does is, the dislocation attempts rather to move around the precipitate. And finally, so it attempts to move around the precipitate. And finally, it moves away from this particular precipitate is by leaving a section of the dislocation line around it, and then it moves. So it leaves behind a section of the dislocation around it. So it will, the intermediate state between moving around the section of the dislocation will be of this form. So between these two, you have a state wherein the dislocation will have the dislocation line will have a shape of something like this, and since these two sections are propagating in different directions, and the magnitude of the same, they annihilate with each other and thereby ultimately leave behind a loop surrounding the precipitate. And so between these two stages, you have a stage wherein the dislocation is of this form, and as it moves, these 2 points, they get together, this point A and B, these 2 points here, they come closer, and when they come closer, they annihilate with each other and they lead to the detachment. So when your precipitate has an incoherent interface, then what essentially happens is that the dislocation tries to move around it, and it leaves behind a section of the dislocation. So again, what we essentially have is the dislocation, it changes its path. So even though we don't have a definite strain energy interaction or elastic interaction, we change the path of the dislocation, and we also need to have a detachment action here. So we need to have a detachment action here in order to separate this particular loop from the propagating dislocation line. So what essentially happens is when a dislocation line meets and a dislocation meets an incoherent precipitate, it propagates in such a way that it leaves behind a loop. Now to form this loop, there needs to be a detachment in the dislocation line. So you not only change the path, so by this interaction, the interaction of a dislocation with an incoherent precipitate, one, you change the path of the migration. Secondly, you need to have an action of detachment. And the driving force for both these is associated with, so the driving force that initially governed the propagation of the dislocation, now it's being dispersed, or it's being used to change the path and to detach the loop from the propagating dislocation line. So because of this consumption of the driving force, there is not sufficient driving force for the dislocation to propagate in the same rate. So you are now consuming the driving force to change the path and to detach and form a loop around the incoherent precipitate. So there is not much driving force available for the dislocation to propagate in the way it should, or in the way it did earlier. So therefore you have ultimately impeded the migration of the dislocation. And therefore ultimately you have reduced the amount of plastic deformation at a given instant during the steady state condition, and ultimately you have enhanced the creep resistance. So in the previous case, in case of coherent precipitate, the ways the dislocation is impeded is one, by the elastic interaction, strong elastic interaction, and the other way is by the fragmentation or the interaction between the particle and the dislocation, not between the interface but the particle and the dislocation. So this interaction leads to the fragmentation, and because of the fragmentation the driving force is consumed, and therefore the rate at which the dislocation propagates is largely compromised. In case of incoherent particle, what we essentially have is a change in the path of the dislocation, and there is also a detachment event that is involved, and because combinations of these two ultimately consumes considerable amount of driving force that pushes the dislocation, that governs the migration of the dislocation, and therefore the rate at which the dislocation migrates is considerably decreased. Therefore the plastic deformation is also considerably reduced at a given point, and ultimately you have enhanced the creep resistance of the material. Now we consider, or we define, the way we define semi-coherent interface is the one wherein the continuity is established by the presence of certain defects. So that is how we define semi-coherent interface. You have continuity, the semi-coherent interface, but this continuity is established by the presence of some defects. So these defects are usually other dislocations. So these are sometimes referred to as the misfit dislocations. So these misfit dislocations are present in order to bring about, continuity in other atoms between the two phases. You have atoms in two phases, and there are continuities in some regions, and there are these dislocations. So these dislocations are present in order to bring about this continuity, and they are associated with the interface. So when the propagating dislocation meets with the semi-coherent atoms, so there is an interaction between already existing misfit dislocations and the propagating dislocation, and therefore this interaction impedes the rate at which this dislocation, the propagating dislocation, moves. So this is in addition to the other ways that movement of the dislocation is entered. In case of semi-coherent interface, you have this misfit dislocation that is present in the interface. So in order to achieve a continuity of atoms and the continuity in the arrangement of atoms, there are misfit dislocations that are introduced in the semi-coherent interfaces. So while the propagating dislocation reaches the semi-coherent interfaces, it interacts with the existing misfit dislocations, and therefore their propagation is impeded. So these are the different ways. Now it is important to note that this loop that is formed surrounding the precipitate is referred to as the Oro-1 loop. So we saw Friedel cuttings, we saw Oro-1 loop, and depending on the nature of the dislocations, nature of the precipitate, either of these two can happen around the semi-coherent or in the semi-coherent around the semi-coherent interface, or in the semi-coherent precipitate. Largely it will be Friedel cutting, or it is also possible to have Oro-1 loop where the number of misfit dislocations are higher. So either Oro-1 loop or Friedel cutting can happen when the semi-coherent interface is present. So in all these three cases, because of the interaction not only between the dislocation of the interface, but the dislocation and the precipitate as a whole, the movement of the dislocation is impeded. Dislocation, while propagating, meets this particle. This particle, first it meets with the interface, there is an interaction. And after this, this propagating dislocation meets with the particle as a whole, and there is another interaction. So both these interaction impedes the rate at which the dislocation propagates. So this is not only for glide event, this is also for climb event. The same happens for climb event as well. So interaction between dislocation and interface, interaction between dislocation and the particle as a whole. Both these collectively impede the movement of the dislocation, thereby reducing the plastic deformation at a given instant, thereby enhancing the creep resistance. Now finally, it is also possible for us to enhance this the creep resistance of the material by governing the grain size of the material. Now at ambient temperature, we can reduce the grain size in order to increase the strength of the material, because grain boundaries as they are, they impede the propagation of the dislocation, and therefore they enhance the stress of the rather the strength of the material. You would need more amount of stress to bring about the same amount of plastic deformation when you have two different materials or you have the same material of varying grain size. So when you have a material of smaller grain size, you need to impose an additional amount of stress in order to bring about the same amount of plastic deformation that you observe in the larger grain size material. So when you reduce the grain size, if D is the grain size, when you reduce it, the strength of the material it increases. So each strength of the material it increases because of again the interaction between the dislocation and the grain boundaries. When you reduce the grain size, you are ultimately increasing the density of the amount of grain boundaries that are present in a given volume. So you are increasing the density of grain boundaries, and therefore the probability of dislocation interacting with the grain boundary increases. So that means you are impeding the propagation of the dislocation, thereby you are restricting the plastic deformation. The same cannot be said for high temperature, or same approach cannot be used for high temperature application. You cannot impede the dislocation just by increasing or reducing the grain size and increasing the grain boundary density. You cannot take the same approach. You cannot do the grain boundary strengthening or grain size strengthening directly at high temperature. The primary reason we cannot do that is because of the grain boundary sliding. We saw in the previous lectures that when you have a grain boundary, so the grain boundary is nothing but the interface that separates two crystalline grains. So therefore, the grain boundary in itself is not crystalline in nature. And when you rise the temperature, it behaves like a Newtonian viscous fluid. So therefore, when you have a grain boundary at high temperature, which is not crystalline in nature, it behaves like a highly viscous fluid and it begins to glide under the given mechanical condition. So therefore, to increase the strength, like in the ambient condition, if you reduce the grain size, you increase the grain boundary density, and therefore you make the material more susceptible for the grain boundary sliding. And that is the reason why we cannot directly use the grain boundary strengthening for high temperature. You cannot increase the creep resistance by decreasing the size of the grains. However, alternatively, you can enhance the grain boundary or rather we can enhance the creep resistance of the material by decreasing the density of the grain boundaries. So what I mean by that is, when you have grains of relatively larger sizes, then the amount of grain boundaries that are present will be relatively low, and the possibility of grain boundary sliding is rather controlled. So you need to have a combination or the interplay between these two factors. One is when you have larger grains, the interaction between dislocation and grain boundary is restricted. When you have larger grains, the amount of grain boundaries that are present will be less, and therefore the interaction between dislocation and the grain boundary is restricted. So therefore the dislocations are not much impeded. So when the grain boundaries, they impede the propagation of the dislocation, and when the amount of grain boundary is low, this interaction is not it's not much probable. So it will grain boundary restricting the moment of the dislocation is rather confined. However, when you have larger grain size and the amount of grain boundary that is present is low, the grain boundary sliding, which also affects the overall creep behavior, can be controlled. So therefore, the grain boundary plays it produces a dichotomy here. One is grain boundary, when it is when the density of it is low, the interaction of it with the dislocation is reduced, and therefore the dislocations are rather free to move. But when you have higher density of the grain boundaries, then the material becomes susceptible to the grain boundary sliding. So the choice of the average grain size, or the choice of the grain size, or the choice of the grain boundary density should take into consideration these two different factors. One, it should take into consideration the interaction between the dislocation and the grain boundaries that impede the movement of the dislocation, and thereby enhancing the creep resistance. And the other factor is the grain boundary sliding. When you have an increased amount of grain boundary density, the grain boundary sliding will be more prominent. So the grain size, or the amount of grain boundary that is present in a system that is used for high temperature application, should be an average, or should be between these two considerations, should balance these two considerations. Larger grains, low grain boundary densities, meaning the interaction between the dislocation and the grain boundary density will be low. So therefore the dislocation will not be much impeded because of the grain boundary. However, when you consider the other condition of smaller grains, there will be huge amount of grain boundary densities. It will become more prevalent to, or susceptible to, the grain boundary sliding. So therefore, a balance has to be achieved when you want to have a high temperature material, high temperature polycrystalline material. The grain size should consider the balance between these two parameters. So with this, we have considered three different ways of considered three different ways of enhancing the creep resistance of the material. One involves solid solution strengthening, the other involves introducing the second phase, and finally by working on the average grain size of the materials. So by thoughtful consideration of these three parameters, we will be able to enhance the creep resistance of the material. So to compile it all, we have seen high temperature materials, what it means when we say high temperature, or what it means when we say high temperature application. We saw how the properties of the material changes with the temperature. We saw how mechanical behavior and the corrosion behavior, particularly oxidation behavior, is influenced by the temperature. And finally, we saw how it is possible for us to enhance this high temperature behavior, particularly the high temperature behavior of the material, mechanical behavior of the material. And these are the ways, or we have considered at least three ways by which it can be done. So with this, like I said, this will be the last lecture, and with this course on the high temperature material comes to an end. I hope you are able to understand, or you are able to relate at least different factors that are involved in the high temperature operation of the material. So I wish you best of luck, and we'll see if possible, we will see ourselves in the other courses. So good luck. I hope there was some degree of knowledge that was imputed through this course. Goodbye.